Hello and welcome to the final video in the mechanics topic. So we're going to look at our last approach towards any mechanics question. So we've had three approaches so far. So we either first look at forces, we look at suvat, we look at momentum, or now we look at energy. Okay, and those are your four tools in your toolkit to approach any kind of mechanics question. Okay. So, first we need to look at energy and what types of energy are we going to encounter in this mechanics topic. Now, the two that we should already be familiar with are kinetic energy and also gravitational potential energy. Okay, so these are the major two that we're going to encounter. So we have kinetic energy and gravitational potential energy. We should already be familiar with some equations for these two in order to quantify them. So kinetic energy is a half mv squared, and gravitational potential energy is m times g times h. Okay, these two can be found on your formula sheet. Okay, but I will talk through these in more detail. But we first need to look at some more examples of energy that you might encounter in the mechanics topic. Because mechanics itself is quite a broad application of physics, we can actually rope in many more different types. So usually they will also make you look at electrical energy. So you might, for example, have a motor that's pushing a car or a wheelchair or a scooter or something like that. And you will then need to equate the electrical energy to the mechanical energy. And what I mean by mechanical energy are just these two. These two are what we refer to as mechanical energy. We could also look at elastic potential energy. This is something we will look at in materials. And elastic potential energy will be more when we look at things like springs or wires or stuff like that. But these are the most common four. It's not only going to be these four that they equate. When you come to do A2, there'll be more introductions of types of energy. You'll be able to go through those as well. So you should be able to show that energy itself can always be equated to different forms of energy. And that is our fundamental law of physics. So I'm gonna label it the golden rule. So if we were to ever break this rule, we would have basically destroyed our understanding of physics. And the golden rule is that energy cannot be created or destroyed. It can only be conserved. It is just transferred from one form to another. Okay, so the most common two that we'll see transforming into each other in this topic is going to be kinetic energy going to gravitational potential energy. In the case where we have things falling or rising or anything like that, when we look at the equation for gravitational potential energy, so gravitational potential energy is m, which is the mass of the object that's rising, times g. Now g is a physical constant, that is 9.81 meters per second squared. This is the acceleration due to gravity on the surface of Earth. And h is the height above the Earth that you are. So this means the higher you are, the more gravitational potential energy you have. It's essentially, a way you can think about it is how much potential does it have to fall, right? If you're on the surface, you have no potential, so you have zero gravitational potential. If you're then 10 meters in the air, you have the potential to fall, so you have some amount of gravitational potential energy. Okay, so gravitational potential energy basically describes how high you are off the surface of the Earth. Kinetic energy is when we're describing things that are moving. So we have half, and this factor is just there for integration reasons for anyone doing maths. M, which is the mass of the object, times v squared, where v is the velocity of the object. So it means the faster the object goes, the more kinetic energy it has. We can usually equate these two, and what we'll find when we equate them, so let's say we start with an object, let's say this is ground level and this is where the object starts, and these are 10 meters apart, okay? And we want to know how quickly, so at this point here, what is v going to be? That's our objective. So we can say, we could do this a few ways really. We could say suvat, we could do that. We could say momentum, possibly. However, we could also just equate energies. We could say mgh, so the amount of gravitational potential energy it starts with has to equal the amount of kinetic energy that he ends up with when it's just about to reach the bottom. And you'll notice I haven't given you the mass because the mass will cancel out of this equation. You don't actually need it. I can then rearrange for v squared is equal to 2gh, and you'll see that v is therefore equal to root 2gh. And you'll probably see this formula pop up sometimes when you're solving these equations. Then all we have to do to solve for the velocity is say v is equal to root of 2 times 9.81 times h, which is 10, and this gives us roughly 14 meters per second. So notice how the same way as in suvat, it didn't matter what the mass was, as long as there's no air resistance present, it will reach the same velocity. And I'll leave you to do this by suvat, the same thing, and verify that that is also true for suvat as well. Okay, so this is energy, and again, remembering the golden rule, we can never create or destroy energy. So in any case where you have any energy, it will always be transferred from one form to the other, and you can usually equate those equations in order to make some calculations. Okay, now we also have to work out how much energy is transferred, right? So we have this idea of mechanical energy, which is if we have things that are moving, hence the idea of mechanics is when we have objects that are moving. So mechanical energy we can quantize by a value called the work done. Okay, now work done is probably a familiar term, but what it means is basically the amount of energy transferred. Okay, so the energy transferred. Okay, so in general, we can apply this idea of work done to basically anything. We can always say we've got energy transfer, so we have work being done. But in mechanics, it has a very specific equation that you can use, and that is that the work done is just the force times the displacement, okay? So we apply some force in some direction, so say I had a box here and I displaced it by 10 meters again, and to do that I had to apply a force of 50 newtons consistently for it to move 10 meters in the direction of the force. Therefore my work done must be 10 times 50, which is 500, and this is joules because it is a measure of energy. Okay, now I mentioned something important, but I want to reiterate: the force and the displacement have to be in the same direction. Okay, they're both vectors, so if they're not in the same direction, then we'll end up with some factor of an angle between them, and we'll have to resolve the force along an angle in the same direction. Okay, so in your formula sheet you don't get given this formula. Instead they added an extra term onto it, and that's for the reason of the general case. So it's not always the case where if I add a force, the object will move in the same direction of that force. For example, a very common example is a suitcase. So if I have a general suitcase here, right, and this is the handle, I'm pulling the suitcase in this direction. This is my force, but actually the suitcase is moving in that direction. It's rolling with me, but actually the tension in the suitcase is going to go up the rope, up the ramp, or the handle, or whatever you want to call it. Okay, so in this case, we're still transferring energy because it's still going to move, so we still have kinetic energy transferred, but we can't follow this equation because they're not in the same direction. So we have to actually generalize this, and we need to work out an expression for the force component in this direction. Okay, now what we can probably say is that this is definitely going to be at some angle to the horizontal. Okay, and this angle I'm going to call theta. Okay, and let me get rid of that line. So it's going to move in this direction, S. But this angle theta means that if I then wanted to resolve for this force, F will be equal to F cos theta, okay, in the direction of S. And I'll leave you to prove that for yourself by practicing your resolving forces information. That means if F is now F cos theta, then I can substitute in work done is actually F S cos theta, where theta is the angle between the direction of force and the direction of the displacement. Okay, and this you can apply to any situation. You can prove also that this still works if theta equals 0. So if they're in the same direction, theta is equal to 0. So this is F and S. So theta equals 0, and cos of 0 is 1, which means this term goes to 1, and then this expression turns back into the original expression we talked about. Okay, now the last thing that we can look at is the idea of power, and what power is and how we can quantify that. So power is just how quickly do we actually transfer energy. So if we're transferring energy, it has to happen over some time. But in some cases we can transfer loads of energy really quickly, and in some cases it's more of a slow burn, and we have a small amount of energy but it takes a very long amount of time. So power is actually the work done, so the amount of energy transferred over time. And again, this is your general expression for it. Okay, so this can be applied in mechanics, electricity, any other thing where you want to talk about power, but it will mostly be between mechanics and electricity. And this can then be used in this idea that the higher the power is, the more energy we're transferring per second. Okay, and if we have a store of energy, so for example a battery, we want it to be rated at high enough power so that it will transmit enough energy, but not so high that it gets rid of all its energy and we have to keep recharging the battery every 5 minutes. Okay, so this is your general idea of power, but this is not the only expression for power that you will be given. You will also be given an expression in terms of force, because we can always link everything in physics together. And so what we've just said is that power is equal to, and we said the work done is force times displacement divided by the time, and we know that actually displacement divided by time we could just say is velocity. So actually we could also say the power is the force multiplied by the velocity, and this is a second equation for power. Okay, so we can do this also. Now from here we are always going to transfer energy. However, it's not always completely useful. We know for a fact if we turn on an engine, we want kinetic energy, ideally, because we want the engine to move. But you can hear it. You can hear an engine revving, so you're getting the excess energy is coming through sound waves. Okay, so actually we need to talk about how efficient is a machine at transferring energy. So the other thing we can say is efficiency. Okay, and the efficiency is, I'm going to call it percentage efficiency. This is not the way it's written in your formula sheet, but I feel like percentages are just easier to acknowledge, to understand physically. The percentage efficiency is the useful energy output and actually I'm gonna get rid of this energy because we'll actually be able to let's just call it useful output for now, divided by the total input. Okay, and then to make it a percentage we times by 100. Okay, in your formula sheet you won't be given the outer part of the percentage, you will just be given the efficiency is the useful output divided by the total output. Okay, in order to make it percentage you just have to times by 100. Now why did I get rid of that E? And that's because I can think about efficiency either in terms of energy or in terms of power. Okay, because at the end of the day, if I'm running a system, the only difference between the energy and the power is how long it's being run for. But in both cases here, they're going to be running for the same time. The input happens over the same amount of time that the machine is running. So you can either think of this as useful power output or useful energy output. And the same with the total input, total power input or total energy input. Doesn't matter which one. So it can be power or energy, which I'm going to note as W for energy transfer. Now, for example, what I mean by this is let's take a light bulb as another example, and this is something that we call a Sankey diagram. Now, Sankey diagrams you might have seen before, but probably haven't heard the name. And this is where we have the total amount of energy. So let's, for example, say we had 200 joules of electrical energy coming in to the light bulb, and we end up with let's say 40 joules of energy going to light energy, which is the useful energy because it's a light bulb, we want it to light up. And then we get the rest of it actually comes down here and comes out in the form of 160 joules of heat energy. Okay, so this is one way we can represent how efficient something is. Notice how I've done these all in terms of energy. If I turn them into power, I would have them in units of watts, but the equations would be exactly the same. So if I wanted to calculate the percentage efficiency of this, the percentage efficiency is going to be the useful output, which is 40 joules, divided by the total input, which is the 200 joules coming in, times by 100, which is 20%. And unfortunately, this is going to be probably the most common kind of percentage efficiency you're going to get. It's very difficult to make efficiencies higher than like 50%. And when we look at thermodynamics in the second year, we might have a look also at the efficiency of thermodynamical cycles. So this has been mechanical cycles. We can also look at engines and refrigerators and try and look at the efficiency of cycles such as that. Okay, but this now concludes mechanics and everything you need to know. Again, if you want to get a good grade, you are going to have to practice. This isn't just a content-based subject, this is an understanding and applying your knowledge-based subject. So I recommend you go away. If you need to rewatch the videos, go ahead. Just make sure you're attempting as many practice questions as possible. And if you get them wrong, make sure you go back, check where you went wrong, and try and correct your mistakes. Thank you for watching.